Welcome you all to the next class in Inorganic Chemistry of Life Principles and Perspectives. So, in the previous 2-3 classes we have been going through the tutorial queries where I am giving insights into that, of course also referring you to look back into what I taught in the class. So, we were in the halfway with the iron in biological systems. Let us start looking at some more queries in iron in biology. Okay, so in the let us look at this particular query. In the protein transferrin, it is a transferrin, is a protein. The binding core has contribution from 2 tyrosine, 1 histidine and 1 aspartic acid. So, this is the, which means this is a primary coordination core. However, when an apotransferrin is titrated with iron 2 plus, no binding core is formed unless otherwise the carbonate ion is present. So, what is this and how do one interpret this one? Okay, if you look at the fully formed protein structure, you will find very nicely from the crystal structure it is understood that the transferrin in the ion center is bound to 2 tyrosines and 2 histidines and even aspartic acid. So, now you take the transferrin, remove the iron. Now, you start adding the iron, it will never form the transferrin protein because of the absence of the carbonate. So, carbonate is required. So, when you add carbonate, what will happen? When you add carbonate, it will form the core, actual core. So, that is the iron core for the transferrin. So, why? Because the carbonate acts like a allosteric factor. So, allosteric means allo is other, steric is stereoform, other stereoform. That means it affects on the stereoforms of this protein. So, with that it will close the core and makes the iron to be present in the transferrin core and make an enzyme. So, that is where, so this is known as allosteric factor and this is the reason why. Otherwise, the core is open, when the carbonate is there it will lock the core. So, therefore, you have the primary coordination core is being completely locked into that. Okay, let us come to the next question. Formation of ferritin from its apoform and the release of the ions from the hollow ferritin occur in an orderly fashion. Explain how. You know that the ferritin core is a huge, it is about 70 to 80 angstrom diameter, about 7 to 8 nanometers diameter, and therefore, about 4,500 ions can sit inside this core. So, if that many can sit inside the core, obviously you have to have a method, you have to have a proforma, you have to have a fashion by which this can be connected. And these are chemical species, these are charged species, therefore, you require, see, if you want to put 2 ions, one next to the other, both are cationic, they will repel. So, how will you do? Put something in between, let us say an oxo or a phosphato, something of that kind, then the oxo will be negative charge, then this negative charge can compensate their positive repulsion and can bring together. And all this thing will go in a very nice orderly fashion. So, as it goes inside, it will attach one to the next, to the next, to the next, the whole thing get. When you are releasing again, the last one will come out first, then the next one, the next one, the next one. There are some more queries where I will give more deep responses to how it happens, etc. Okay, what is the form in which iron is stored and what is the form in which iron is released in case of ferritin and how and why? See, the transport when it brings, it is always in the iron 2 plus, and when the iron 2 plus goes, it goes through the channels and goes inside. When it goes inside and binds to the carboxylic framework, then it will get oxidized. For oxidation, O2 is also used. Okay. And when you want to reduce, when you want to release, again the iron which is oxidized form of the iron, oxidized form of the iron is bridged by oxo and phosphato groups, therefore, it will not easily come out. Also, you know that iron 3 is less labile than iron 2. Therefore, you need some reducing agents which will reduce the iron 3 plus to iron 2 plus, and once it becomes iron 2 plus, it is mobile and labile, it will come out. That is kind of thing. Okay, let me bring your attention to the next question. In ferritin, while some of the channels are hydrophilic, others are hydrophobic in nature. Provide the reasons. Why some of them should be hydrophilic, some of them are hydrophobic? Very simple. Without even knowing any aspect of it, can tell. That means there are some hydrophilic loving groups either to go in or to come out. Similarly, some hydrophobic kind of a groups to go in or to come out. That is precisely the reason. The channels are there to take in or channels are there to take it out. What are the advantages of the presence of such hydrophobic and hydrophilic channels in ferritin? Yes, there are several advantages, because what is required? You have to have iron 2 plus to go inside, you have to have some O2 should go inside, you have to have reducing agents to go inside and to reduce and take it out. So, therefore, entry and exit of all this, and the iron entry and exit, as well as the hydrophobic as well as the oxygen entry. So, all of these uses either the hydrophilic or the hydrophobic channel, therefore, both of these are essential, and you can get all the details from the information that I have given in the class. Okay, let us come to the next question. What is the easiest method to identify whether the given iron sulfur protein in rubidoxin or the ferridoxin? So, what is the easy method to identify that something is missing? The inorganic sulfur or sulfide. So, what is the easier method to identify sulfide ions whether given iron sulfur protein is rubidoxin or ferridoxin? Okay. So, how do you find? In the rubidoxin there is no S2 minus, in the ferridoxin there is S2 minus, and if you add mineral acid, the S2 minus will come as H2S, and the smell itself will tell you that there is a inorganic sulfide. In the rubidoxin you take and add HCl, nothing will happen, no smell will come, because there is no sulfide ion. Very simple, no spectrometer is required, you can do that. Let us look at some more iron in biology. How does cytochrome P450 give regio and stereospecific product in case of camphor? Camphor oxidation I have already shown in the class. As you know, the camphor is held by the secondary interactions of the protein at the cavity above the porphyrin heme level, such that that particular carbon is poised exactly on top of the iron center. Why? Because that iron center will become ferryl oxo, and that oxo group will go from there to the carbon center, and also the direction. So, since the position and direction both are fixed by the protein, in arranging the substrate exactly over the iron center, therefore, this is where you get the regio and stereoselectivity. Okay, come to the next question. In cytochrome P450, if the electron is involved in the activation of the enzyme instead of the substrate, there will be a havoc. What is this havoc? How will this happen? Okay, so let us look at the query of this one. In cytochrome P450, if the electron is involved in the activation of the enzyme instead of the substrate. So, substrate is camphor or any kind of other thing, and if that happens, then what we say is it is really going to be a dangerous part. Why? Why is it dangerous? Because once the enzyme is activated by one electron reduction, this electron can be given to the O2, and the O2 can become O2 minus dot. And you know the O2 minus dot is superoxide and it is dangerous. It can oxidize the substrate, it can oxidize the enzyme itself, because the substrate is not there. Okay. So, therefore, the enzyme has chosen that it is activated only when the substrate comes, not by the electron. Okay. Let us get to the next question. in cytochrome P450, what is the nature of the species formed which are involved in transferring the oxygen or oxo species to the substrate? Is the ion center which will become ferryl-oxo, and it is the ferryl-oxo which is oxidized from the ion which transfers the oxygen. What is the phosphatase activity? Why is that there are two metals in this? So, what is the role of the bimetallic center? So, the phosphatase activity, purple acid phosphatase, and you have alkaline phosphatase too. In purple acid phosphatase it is mainly iron, in the alkaline phosphatase is zinc ions. These are all the dinuclear centers. So, in the phosphatase activity, means the phosphate ester hydrolysis. So, hydrolyzing the phosphate ester, that is what the thing is. So, what is the role of the two metal centers? One of the metal center will be useful in binding the phosphate moiety. The other one is useful for providing a nucleophilic attack on the ester, so that the ester gets hydrolyzed. So, one is for binding, other is for catalysis activity. So, both are together as a binuclear. Come to the next question. What is the role of dinuclear center in ribonucleated reductase? We have seen the dinuclear role in phosphatase. So, is it the same in this case? So, is this the catalytic center? The role of dinuclear ion in ribonucleated reductase is not same as the phosphatase, because no substrate binds to the iron and no second iron will be acting as a catalyst. Its role is what? I am sure if you look back you would see that to stabilize a radical on the tyrosine. That tyrosine radical will trigger the reaction basically. So, therefore, in case of the ribonucleated reductase, the iron neither provides a position for binding the substrate, nor second iron provides any utility of catalytic activity at all. Okay? So, therefore, the di-iron center present in the ribonucleated reductase is not the catalytic center, it stabilizes the tyrosine radical, and reaction occurs elsewhere in another subunit of this, where this radical is transferred to a thiol radical, and from there actually the reaction takes place at the center where nucleotides are bound. So, I hope you understand the things. Let us look at some additional questions. These questions based on the nickel in biology. Enzyme urease is a hexamer with a molecular weight of 600 kilodalton. Let us say that 1 micromole of this enzyme is incubated enough period with 6 micromoles of nickel 2 plus salt. What percent of urease activity does this enzyme exhibit under such conditions, and why? See, if you look back, also given in the question is hexamer, 600 kilodalton, about 100 kilodalton for each monomer. And you know each monomer has got one center of the nickel center, one dinuclear nickel center. This is a dinuclear nickel center. Okay, so if you use 1 mole of enzyme, what does it mean? There is 6 equivalents of subunits. So, it is basically 6 mole of nickel 2 plus, and that is what is, you understand that. So, the entire 1 mole micromole is of protein is saturated with the nickel, 6 moles. Okay. So, what percent of urease? So, how much moles of nickel is required actually for 1 mole of micromole of enzyme? Because each center is dinuclear, there are 6 centers, 6 into 2 12, but what we given? Only 6. So, that means you get only 3 of them. So, therefore, the percentage of the reaction, what percentage of the urease activity does this enzyme exhibit? So, 50% under such conditions in that. So, you put all 12 micromoles, then the whole thing, all 6 centers are occupied by nickel, and then you have a nickel enzyme functioning fully well. What is the role of bimetallic nickel center in this enzyme urease? How is the substrate urea is recognized by the enzyme urease? This is more or less like the kind of an answer I gave for dinuclear manganese center present in, or dinuclear ion center present in phosphatase. So, what did I tell there? One of the ion center is providing a space for binding, other ion center is providing a nucleophile to attack, and thereby you have a cleavage, exactly the same. So, one of the nickel center is useful for binding the urease, the CO moiety of the urea, and the other one provides it's an attack, and this therefore you have a cleavage of the ammonia. Finally, you have to cleave the urea to get ammonia and the corresponding carbonate equivalent one, because the water is also involved. You can see the reaction in the thing. Let us look at the next one in the copper. The copper in biological systems. Why are the type 1 copper enzymes a blue in color? What are the special features of these enzymes at the active site? So, whenever you look at the inorganic compounds and you look at some kind of color, there are 2 reasons. One is either through the DD transition or through the charge transfer transition. The kind of a transition that you expect here will not be in the DD transition, will not be in the visible region, therefore, it is the charge transfer. So, where the charge transfer from? If you are aware, this has a cysteine and methionine, therefore, it is a thiolate function or sulfhydryl function or thio function. Therefore, it is from the thio or thiolate to the copper center charge transfer, and that is what is found. What is the major function exhibited by type 3 copper centers in proteins and why? First of all, the type 3 copper center is a dinuclear center. The dinuclear center, the moment comes in the mind, one should think of both the metal centers for a redox purpose, giving 1 electron. In fact, copper 2 can go to copper 3 can go to copper 2. So, 1 electron. So, therefore, 2 such copper centers, 2 electrons. Therefore, one can expect a 2 electron redox process. So, for a O2, 2 electron redox process is O2 2 minus. So, the major function exhibited by the type 3 is activating the oxygen, and then followed by your oxygen transfer, etc. takes place. Okay. Let us look at the next one. What is the bimetallic center present in copper zinc superoxide dismutase? CuZnSOD. How does this function? During the function, what are the notable features? What is the bimetallic center present in the copper zinc superoxide dismutase? It is copper and the zinc. It is there in the name. How does it function? Can you expect zinc to undergo redox? No. It is a redox silent, and it is always known as zinc 0, zinc 2 plus. So, zinc 2 plus will never change, whereas copper can go between copper 2 plus and copper 1 plus. In some situations, copper 3 plus is also possible, but not here. So, copper 2 plus, copper 3 plus. So, therefore, it is basically the copper undergoing redox will bring the redox, though the zinc is present in that. So, that means zinc should be a silent element, or it could be a what you can call it is a structural element, and copper is a functional element. So, the function is occurring at the copper and the structure is stabilized by the zinc. The question is not there, but I will pose, how do you know that it is the one is catalytic, other is structural? Suppose you replace the structural element of one by another, the activity may not get affected to too much extent. On the other hand, if I happen to replace the catalytic element, a catalytic ion, the catalysis will go down dramatically. So, therefore, you can easily make out what it is. This is not there in this question, but I am posing another question on the spot now. Which one of the metal ions, copper, zinc, is catalytically important? I already explained to you in the previous, it is the copper which is catalytically important, zinc is structurally. What is the main role of tyrosinase enzymes? How does the oxidation of orthohydroxyphenols to orthoquinone occur by the enzyme tyrosinase? Okay, tyrosinase, tyrosine oxidation. Okay. So, that means these basically oxidizes the tyrosines, they can oxidize the aromatics, all these kinds of things. So, these are tyrosinase kind of enzymes, and this enzyme has got 2 copper centers with 3 histidines and copper 1, no bridging. Now, when the oxygen comes in the picture, the oxygen will be activated between the 2 coppers by giving 1 electron each and making it to O2 2 minus, and coppers will all get oxidized to the corresponding copper 2 plus. The tyrosine or hydroxyphenols which bind at the copper center will be oxidized by this one. In fact, this kind of a thing is a chain kind of a reaction that occurs in the biological system, and such things are always found to lead to, when so many enzymes work, to lead to something called melanin formation, skin tanning, etc. Cut fruits brownishing, etc. So, what is the role of the copper centers in ascorbate oxidase? There are 3 copper centers. What is the role? Type 1 copper provides electron transfer. Type 2 POTS mediates. Type 3 activates the oxygen, and this oxygen is further broken, and you form the oxygen with a tricenter, 1 type 2 copper, 2 type 3 coppers. So, it will become a kind of a bridge species where the type 2 copper will help. So, type 1, type 2, type 3 coppers. Okay, we have some more questions I will take in the last class, that is the next in the next class. I will take the remaining tutorials and sum it up. Thank you very much.